SEPTET project stands for Sustainable Energy Pathways Through Engineering and Technology. And the goal of this project was to bridge multiple disciplines together, such as not only engineering technologies, not only engineering sciences, but also social sciences, arts, digital media, and social outreach to general public. Sustainable energy pathways can be described in a way that the way we use energy should not harm or should not make the life of our generations, of the generations after us, any worse than our own. In our case, a specific energy source is solar. On top of that, we're trying to combine other energy sources that are always present around us, such as RF coming from either cell phone towers or TV towers, Wi-Fi coming from our Wi-Fi hotspots. We're also trying to combine thermal sources of energy, such as extreme heat. So currently, silicon-based photovoltaic devices or solar panels are limited to about 25%. Our goal was to improve the efficiency of specifically silicon devices. So we wanted to bring out an idea to a regular consumer understanding of how much power is really consumed in their house, what can they do to improve, what can they do to conserve, and what can they do as a global society to think about sustainable ways of living.
I'm Sang Han, professor in the Department of Chemical and Nuclear Engineering. Our group is focusing on harvesting energy from the infrared spectrum. Society has progressed to such an extent that we're using a lot of mobile devices. They typically communicate using infrared. When you use the remote control to turn on and off your TV, that's exactly infrared signal. I think we can harvest these communication signals and turn that into a useful energy. This is a cross-sectional view, schematic view of multi-junction solar cells, and they are typically used on satellites. What you see on rooftops, they're silicon-based, and these photovoltaic devices will not last very long out in the space because of the space radiation. Roughly, to estimate about a square foot block with the focused sunlight can produce enough electricity to power your entire house, typical average house. So these cells actually are today probably the most efficient solar cells, about 43% or above, but they're expensive. If you can actually keep them connected electrically by having strong metal lines, then potentially can ensure the longevity of these solar panels. But the solution requires not just understanding of my own specific discipline that I grew up in, but rather requires knowledge and skills from many different disciplines. Today's problems are that complex.
My particular research involves growth of 3-5 semiconductors. That's our primary role. When you do start the process, you start from a seed crystal, which might be a tiny crystal, and you grow large boules out of it. They're then diced into discs, which are wafers. We then take these wafers and grow subsequent layers, one layer at a time. In this case, it's one atomic layer. Anytime you decide to grow crystals in a reactor, you have to be very careful about the purity of the material. You do not want stray atoms, and hence the ultra-high vacuum. The reason that semiconductors are a special class of materials is the periodicity of the structure. So you notice that this particular structure is highly periodic. It forms some interesting shapes. Now it's a hexagon, and you rotate it a little more, it forms a very different shape. You can look at it this way, again a different shape. So the periodicity of the structure is rather critical. You take these solar cells, for instance, if this were your cell, you glue it to a handle like glass, you flip it over, and you etch off the substrate. So now it's inverted, and it has multiple junctions, so it's called inverted metamorphic multi-junction solar cells. You know, in the long run, if you develop harvesting technology, you'll be surprised by how much energy you can recover instead of just wasting it.
It's a very promising way of how the light manipulation will progress in the future. Our project is about creating a photonic crystal, which is a structure that can manipulate the light. For the SEPTET project, we used a structure called inverse opal structure, and this structure has the property which is called photonic band gaps. In the photonic band gaps, the light that has a specific range of wavelength will be absorbed more prominently. And by varying the structure of the inverse opal, we can choose which wavelength that can be absorbed. The first part of the project, we need to create opal templates. The second part of the project is to fill the gaps. And then after we fill the voids, we can remove the microsphere to create inverse opal structure. The software we use is COMSOL, which can simulate the various properties of the structures. Previously, I don't have any experience on nanotechnology before, so I don't know how to work in a clean room. I don't know how to create opal structures just using the tools that we have. But with this project, I am able to experience that. I really appreciate that the SEPTET can offer me this experience. This project can be a significant part of the progress that we can make in the future.
My part is based on the piezoelectric harvesting and nanofabrication of device, at the same time material that can fit or can be more efficient for harvesting vibration. The grass is the best way you can see how the nanowire grow. You seed and then you start watering, and after a while you see this grass growing and popping up. And more you water, more the grass grow. And at the beginning the grass is very straight, so it looks like very perpendicular to the ground, and after a while start bending, and when the wind blows, bends even more. Just think about when you walk, you move something, and that can be translated into vibration of the ground. The vibration are just a simple example, wave sounds, and those they have different frequency. So if there is a frequency that is more common or more abundant, made by human or made by nature, that is the one that you want to harvest. For example, to illuminate your walk path, you're walking, and you can illuminate the way you're walking. So we can storage that force in another form of energy, typically maybe recharging a battery. When you walk, it's produced. When the wind blows, to produce, because there is movement. Since it's free and it's wasted, when it's not used, why not use it?
Surveys we did showed that people are willing to switch to renewable and sustainable energy sources if the cost benefits work out. We're taking the virtual environments and augmenting them with real data. We're taking data from P&M solar farm, from their wind farms. The main one is this virtual neighborhood. So the idea is that in the neighborhood are these houses that run on virtual solar power, run on virtual wind power. The main benefit is you can experiment, as a consumer, you can experiment with these technologies and without having to bear the costs. We also have it set up so that you can point your phone at a device and look at its wattage, so how much energy it's consuming. Or if you've programmed a schedule for that device, you can just point your phone. And that is augmented reality. And we're trying to build this energy harvester, and it doesn't exist yet. We can pretend it exists as long as we know functional characteristics, how much wattage it puts out. So we can pretend it exists, and then we can experiment with it in the virtual world.
My team's role in the SEPTET project is visualizing energy in a large-scale building-size installation. Buildings are actually one of the largest consumers of energy. If you can reduce the energy consumption of buildings, especially large buildings, you can have a great impact. It's difficult for people in the general public to understand the work that's being done by scientists and engineers. So our role is to try and translate that information to the public.
I've been working on the design and fabrication of the skylight project that we installed here at the Balloon Museum. The aluminum channel is clean looking, and it also is a thermal sink. So by dissipating the heat that LEDs are generating, it gives the LEDs a longer lifespan. I've got a clamp meter to measure the current in the DC and in the AC, and that's drawing a relatively small amount of power.
We're experimenting with interactive visualization where people can use their cell phones to interact with the building. We just want to make the potential conservation of energy and the creation of energy fun and exciting to the general public.
I like the idea of text messaging as a format for interacting with people because it's very low impact, meaning everybody has a phone that they can text with and they don't need a fancy phone. One challenge, but it's also a benefit, is having to learn new things constantly. We had to learn Android in order to figure out how to get and receive text messages, and there's database stuff. And that is a challenge because sometimes you'll get stuck and you won't know what you're doing, you're hacking things together, but then it's also fun and exciting.
I used some open source software. I modified that so that we could generate our own video frame by frame and then send that over to the agencies. I took this as a bit of a challenge to A, improve my own programming by understanding others, and B, doing it in such a way that I can re-release that code and keep it as legible as the original author had made theirs. If you can construct something that it can be used in other contexts, the code can continue to evolve and get better. We set out to do a thing and brought it to completion. I think this is a great example of when everything went right.